Hi. Hello, everyone. Greetings. Welcome. Welcome to Scala Days, Day 2. How many of you guys had a good night last night? Awesome. No? Okay, somebody here is trolling us, I think. No. I hope you had a good night. I hope everyone did. So just want to make a few quick announcements before we announce the keynote. First of all, tonight is a community party. And the beer is being sponsored by Bold Radius, so let's all give Bold Radius a thank you for that. But you can find details for the community party here on your thing. Everyone please attend. It's always a good time, just hanging out with everyone. The other thing is there's a small session change. So at 13:20 there was a Scala code quality talk. Unfortunately, the speakers weren't able to come. So instead, Tal Weiss is going to be filling in with a fixing reactive code at 100 miles per hour, 5 techniques to debug Scala and akka. So if you guys are interested, that's going to be the replacement talk. So make a note of that. It's online, but it's not on your badge because these aren't electronic yet. All right. So with that, I'd like to introduce our keynote. Our keynote is someone who has spent 20 years in the mountains of Sweden trying to find his own mountain for which he could give his name to. But instead, he got sick of that and decided to write an actors framework. So this is Jonas Bonér, CTO, and one of the founders of akka.
Thank you. What an introduction. He didn't say what the mountain was supposed to look like, though. We'll leave that aside. So my talk here is, can you someone swap the slides? Yeah. It's titled Life Beyond the Illusion of Present, and that could be sort of an esoteric philosophical title. And this talk is not really much about Scala. It's actually about time. I found this quote in some research papers I read some time ago. It's like the time is a device that was invented to keep everything from happening at once. So this talk is really about an exploration of time and our perception of reality. So it's sort of divided into two parts. In the first one we discuss the physics and the philosophy and the psychology of time and the way we sort of experience the present. And in the second part, I think how sort of this knowledge then sort of means that we need to change the way we view and model the world in software. And I think across other industries as well, but I'm just going to focus here on software. So I've been sort of spending the last 10-15 years building like large-scale distributed systems, and I've really come to the conclusion that the idea of the present is really nothing but a very stubborn illusion. Okay? Everything we see, feel, touch, hear, really is just echoes from the past. But this illusion has really influenced the way the way we view the world in so many different ways. But I think it was sort of inspired by Newton and Newton's physics, in which we have like the time marching forward uniformly, and where time is something that is absolute, even at a distance. And this was a good approximation, sort of a good model to model what we knew then, right? But we know more now, and I think we, in a way, need to break free of this sort of illusion, and because. But take a step back. I think the reason why we sort of like this way of looking at the world is that it's very appealing to us, right? We humans are really bad at multitasking. We're bad at doing like things concurrently, and think concurrently is extremely hard, right? So it's easier for us to think about time as something that is absolute, and that because it helps us maintain like a sense of now, that we are in control of what's actually happening right now. And I think this model, this view of the world, sort of made perfect sense in early days of computer science as well, when we had single processors, like running on single machines. You know, this is John von Neumann, and he introduced the von Neumann architecture in the mid-40s. And it has this, like, you know, this total ordering of instructions, working on this array of memory, like a word at a time, like fully sequentially. And it sort of assumes a single process working through this array of memory and updating mutable state along the line here, and that you actually are in full control of the present. So these two models mapped very well. And back then, I mean, life was good. But then along came the need for concurrency, and it really made life miserable again. I don't know how many have sort of experienced the same feeling as this comic strip. I've done it way too many times, right? It's just because it started to crack a little bit. I mean, our perceived reality really doesn't match up with how the world is actually working underneath. Then Jim Gray came and saved the day. You know, we got transactions to make sense of concurrent processes, right? It gave us this illusion of ordering within a transaction, while we have disorder across transactions. So it allows us to like maintain this like single system image, like isolation and consistency and all these things, you know, that we have in the database world, like ACID. And what it did was it gave us our linear time back, like our sort of, and in a way sort of an escape route back into the safe zone of Newton's universe, into our comfort zone. So can we go home now? Are we done? Well, no, actually along came distribution again, right? And it made life miserable again, because the problem is that a lot of these techniques do not work well in a distributed system for various reasons. Like distributed transactions are brittle, they don't scale, they're not possible to make them fully available, and so on. And it really, I'll dive in a little bit more why and so later, but it's not really to be surprised about, because unfortunately it's not how the world works. It's really this illusion that's like been running behind us, like catching up on us now, and we can't fool ourselves any longer. So in a way, like the dream has vanished, but the lifestyle, I think, doesn't have to remain. We can actually, I think we can find a more sustainable way of viewing the world and to model it in our systems. The problem here is that there is no absolute present. It's never been, at least not like a globally consistent present. Time is not something that is absolute. And I think that we can, however, I'll try to argue, we can sort of construct a sufficiently consistent local present that we can reason with. And that will give us enough tools to actually make sense of the world. So it's been said, it's an old quote, like the future is a function of the past. The first reference I found to this was an Australian math teacher called Robertson. And the important thing here is that what it says is that the future is a function, like it doesn't change the past. It can only construct a new future, depending on its input. But I would actually rather say that this is not really accurate. The truth is more like that the local present is a merge function of multiple concurrent pasts. You can let that sink in. I mean, to help some of you Scala developers, I actually hacked it up in a little bit of code here. So if we have the observed past, right, it's actually fold left using a merge function over our observed concurrent pasts. Then we can construct a new local present based on the input that we received, that we have observed, and we can reason about that and take action and move on. Perhaps publish new data based upon that and so on. So I think what we need to do is we need to explicitly model the local present as facts. I'll get into what I mean by facts later, derived from the merging of multiple concurrent pasts. So this is like the essence, and I'll try to explain why and how further on in this talk. So it's also important to realize, as we all probably do, I mean, we all agree with this, but we don't think about it that much, that information is actually always from the past. It's when you have sort of observed something, it's already happened, often quite some time ago. Right? This is how we all humans work and think, and we don't. It's nothing specific, special for us. Still, we try to like shoehorn a completely different, I mean, this world into a completely different model where we sort of get rid of these constraints, or try to get rid of these constraints. So we're always just looking into the past, right? So in a way, everything is in the eye of the beholder. It's everything like it's how each one of these individual units perceive the world. And the present is really something that is completely relative to the observer. So in a way, the truth is actually closer to Einstein's physics rather than Newton's physics, where everything is relative to the perspective of the viewer. Where actually with time, one of the fundamental traits is that time is not absolute, but it marches forward actually based on the perspective of the viewer. And it's totally sort of biased, right, subjective. This is actually a picture with Einstein and Kurt Gödel. It's a book cover from a book I read like a couple of years ago now that's inspired some of the ideas in this talk. It's called A World Without Time. It's a really fascinating book. I really encourage you to read it. Gödel, you know, this was his like famous logician, and he actually spent the last like 10, 15 years working with Einstein on physics and tried to make sense of time. It's also true that like, information has latency. I mean, information travels at the speed of light. The speed of light puts a hard cap on how fast information can flow. And you know, that's also like contrary to what Newton said, but that also that Einstein later proved. And it's very much, it's not just some esoteric concept, right, that we don't have to deal with. It's actually, most people that have written systems, large-scale systems, know that this is a fact. It actually affects the way we must like design software today, that information has latency. That's a round-trip time to send data from data center in Asia over to London or whatever, like I mean, Tokyo, London Stock Exchange, for example. Another thing, very important thing to always consider is that the cost then of maintaining this illusion of Newton's universe can sort of be defined in terms of contention, meaning that we're sort of waiting for shared resources to become available. And coherency, which is something that a lot of people don't talk about, is the delay in time for data to become consistent. Most people have heard about Amdahl's law, right? I assume. Amdahl's law explains how the effect of contention can mean that we can have diminishing returns. It's the dotted line there. That's like as we start adding more resources, more processing power to our problem, we don't get the linear sort of growth in terms of scalability. But sort of the bottlenecks that we introduce through contention actually slows us down until it's completely flat, and doesn't matter if we add more resources to the problem. We need to re-architect. But coherency is not something that is not that often talked about. And what's interesting with that is that it actually can be that the cost of trying to maintain this delusion that we're all living, having the same global present can actually mean that you start getting diminishing returns. Actually, when you start adding more processing power to the problem, things get slower and slower and slower. And that is the blue line there. And that is explained by Neil Gunter's universal scalability law. That it's not just some it can't just be dismissed as like computer science math that nobody needs to care about. I think we all need to know these models and fully understand them, internalize them in a way so we don't have to think. We can intuitively think about things like this. But again, it points in one direction, that we need to give up this Newton's universe again. It's just not worth it. The illusion, maintaining this illusion is just too costly. And as latency gets higher, the illusion cracks just more and more and more until it becomes completely useless, as we've seen. And you know, as you understand, in a distributed system, this latency is orders of magnitude bigger than running in a single processor. And now there's distributed systems everywhere. You can't escape that. Most systems today, you use like SQL databases, NoSQL databases, they use replication, have mobile clients that can go offline and come back. You need to sync back the state. And it's really hard to build a system today, actually, that is not a distributed system. They need to be in embedded systems. So, but most of us write enterprise applications like web applications and applications that, solve big problems, need distributed systems. And with the advent of multi-core and cloud computing, right, everything changed. Because now, I mean, everything sort of is distribution, the way I look at it. Either we have multiple cores that runs the application, where we have the different cores like connected with the QPI link, and you need to maintain consistency and coherency across that. Or you have nodes. I mean, in a way, you can look at it like you have cores running in process, or these cores are put on different machines. And then you have the network between. So this also boils down to why we need the reactive principles, why we need to fully embrace message passing at the core, because at the fundamental level is all message passing. So everything you layer on top, trying to pretend that it's not, will just increase the costs. And some abstractions are definitely useful, I'm not saying that, but we need to get into the mental model that there is latency, and things are distributed, even on a single machine. And this again, I mean, we cannot just afford freezing the world just to have this like simpler programming model that often becomes a leaky abstraction that leaks so much that it becomes useless. And we all know that the network is reliable, right? Not really. I mean, when you add the network in the mix here, it's not just latency; it's actually failure. I mean, that you can be guaranteed that things will start failing in the most like spectacular ways. Messages will be dropped, they can be reordered, you can have like partial failures, right? And it's really hard to know what is a failure and what is not a failure. It's actually impossible. It's proved to be impossible to know. You just need to take educated guesses if the service you're communicating with is down, or if it's just doing garbage collection. Or there's a like temporary network drop, and so on. So it's hard actually, but I think good practices can help. I don't know, you might have seen this quote: if a tree falls in the forest and no one's around to hear it, does it make a sound? It's also sort of philosophical question, and sort of the question asked here is like, the way I interpret this is can something exist without being perceived? Einstein once asked Niels Bohr, this Danish physicist, they wrote a lot of letters to each other discussing like topics like this. And in one of his letters he wrote, "Do you believe the moon does not exist if nobody's looking at it?" And Bohr said, "However hard you may try, you can't prove that it does." And this might sound like, yeah, some philosophical, metaphysical questions, no connection to reality. But I think it actually does. I think it directly affects computer systems and the way we need to think about systems, since information can and will get lost. And you know, through network drop packages and so on, everything that can happen when you add a network. But think about it. What if this lost information actually are facts about the past? What does that mean? Does that mean that certain pasts never happened, since we couldn't perceive them? And what does that mean for our present? If our present is our only, if the past is our only path to the present, if certain pasts are not able to be perceived or observed, I mean, what does this mean for our present, really? But one question that can sort of help us answer this is like, how do we deal with information loss in real life? I mean, we do this every day, and we don't even think about it. I mean, for example, in a noisy bar, most people were probably out yesterday, and it might be hard to hear what your colleague or buddy said. What do we do when we only receive partial information? We usually sort of wait a while to see if we get more information to make sense of that, right? Or we ask again, what did you say? Or we might receive the same information or additional information to help us make sense of of what was said. But we do not aim for anything like guaranteed delivery. We actually instead fully embrace naturally like at least once delivery and idempotency, if you know what that is. And we learn at a very early age to fill in the blanks, to actually take educated guesses based on partial information. We learn to fill in the blanks. And if we're wrong, we just take compensating actions. Okay? This is all very natural to us. And I think we need to fully embrace this when we build systems as well. It says we've been spoiled for too long, right? That we live in this fantasy world where life is so much easier, right? And sort of we sort of forgotten about how we actually live our lives and how the world works in many ways. And this is what Pat Hallen calls apology-oriented programming. He wrote a blog post. There should have been a paper. I think it's some nice ideas there. It's called Memories, Guesses, and Apologies. And he argues that all computer science can actually be like sort of defined in terms of memories, guesses, and apologies. Meaning sort of just do something and apologize for it if you're wrong and take compensating actions. And this is, you know, this is how a lot of systems work today. I mean, ATMs work like that. If the ATMs can't contact to the bank, they will still give you the money, and it will then compensate by giving you an interest rate sometimes, but at least deduct it later from your account, sometimes into a negative balance, right? And you owe the bank. Or this is also like why most people have sort of probably experienced if you travel a lot, like overbooked flights. Same here. I mean, the airlines, they know that they won't fill up the plane, so they overbook it, and then they try to bribe themselves off by giving out vouchers and stuff like that. So there's sort of a way of taking compensating actions. So the bottom line is that I think we cannot force the world into a single globally consistent present. It's just too costly. And it's actually not how the world works. So, should we just give up then? I believe that there is a path forward. And that is that we need to treat time as the first-class construct in the programming model. We just can't hand-wave this any longer. It's actually surprising how we've gotten this far as an industry with just hand-waving such a core concept as time. But we do, when you think about it. We have no clue what we're doing, really, when it comes to time, most often. I think it needs to be explicit in the programming model. It needs to be explicit in the languages, ideally. It needs to be explicit in the design and the algorithms that we use, data structures, I believe. So, and we're not there yet. So this is sort of like call for arms in a way, kind of talk. I would like to have more discussions about this. But what is time really then? One definition that I tend to use is like the time is really the succession of causally related events. It's not really about wall clock time, you know, hours, minutes, seconds, and so on. I think that's sort of just a leaky abstraction for us to try to make sense of time. And you have clock skew, and all these problems immediately come in place. But it can be a good approximation for a lot of things, but it's not the essence of time, I think. And I think this is also why when we experience time sometimes just vanishes, you know, flies out the window, and sometimes feels dog slow. If you think about it, why? Why is time sometimes just vanishing, and sometimes like, oh, you just can't understand how slow it's running? It's usually related to the experiences we had, the events that happen, like the causally related series of events. I really believe that time is all about causality, really. It's all about the succession of causally related events. And the question is then, how can we manage time? First, I think the most important thing, or to start with at least, is to think and design and model the world in facts. Facts just simply cannot change. And then ordered facts is less causally related. So what is a fact? Fact represents something that happened in the past. Merriam-Webster says that a fact is something that truly exists or happens, something that has actual existence, a true piece of information. And facts just accrue. I mean, they are values, they are what we call immutable in computer science. And they accrue through either you get completely new facts into the system that you can store away, or you can deduct new facts from existing facts, make sense of the facts that you have. And facts can often be modeled as, and we often do that, like as data, it's like dependency graphs, derived knowledge. And a lot of data structures actually work this way, and I mean, Git works this way, and so on. It's important to know that, to fully embrace that immutability is a requirement here. A fact is not a fact unless it's fully immutable. We need to stand on solid ground here. And the problem with a lot of object-oriented languages, like classic object-oriented languages, is they don't help here much. I mean, Rich Chick has been giving some great talks on this, about how they don't treat, how they do treat value and identity the same. And this is like the problem with variables, right? That they can just change when you're looking at them. I mean, you thought you had everything figured out. You took the decision based on the value of a specific variable, and then you look away, and then you look back, and it has changed, right? It's not the stable ground that we need to actually to do advanced or interesting work on, I think. Immutable state was sort of invented to make life easier, and it did make total sense in the von Neumann architecture, when we just had one sort of process that worked through this array of memory, but it doesn't work any longer. So the question is, do variables have a purpose in life? Variables have a purpose in life at all? John Backus said in his Turing Award lecture already in '77 that the assignment statement is a von Neumann bottleneck of programming languages, and it keeps us thinking a word at a time in terms of much the same way that the computer bottlenecks does. And here we have it again, a word at a time. It tries to like shoehorn us back into the Newton's universe, right? And it implies global mutable state that we've all been taught is actually a bad thing. And this is why we need to, add a lot of plumbing and to guard ourselves as soon as we run this on multiple processors, threads and locks and in concurrent data structures that are safe and so on. So what do I think? I think the mutable state absolutely has its place. It's not just evil, but it needs to be contained, I think. It's great it can simplify things in local computations, but I think they should really be totally isolated like safe havens. And once you're done with the computation in this safe haven and want to publish the result to the world, publish that as immutable facts then, so others can actually reason about them. So how should we manage facts then? I think functional programming is a great way of managing facts. It's sort of functions sort of a fact machine in a way. And when you put facts in, and you get new facts out. And this gives us code that we can trust, that are referentially transparent, things that we all appreciate as functional programmers. Logic programming also is also something that I wish people would pay more attention to. It's a great model to view the world. And it's sort of failed because of the hardware was too slow. Same as like small talk and so. I think it's I hope that it's on the rise. And we're starting to see some really interesting research being done in marrying logic programming in distributed systems, because it has a lot of nice characteristics and properties. I'll just touch briefly on that in the end. Dataflow programming is also great, right? Because that's really what it's all about. It's about like model the succession of time as data dependencies. Facts are derived from other facts, and data flows that way. And futures is like a simplified version of that. Data flow concurrency, like you have, for example, language like Oz and that we had earlier in Akka, is also gives you a great tool to work with that. And then the interesting thing with data flow programming, at least pure data flow programming, is that it's fully deterministic. It will always produce the same result. If you put in 5 and something, this whole data flow graph is resolved, and starts to do its work and you get 3 out, and then you will always get 3 out if you put 5 in, right? So it's because sort of indeterminism is removed out of the picture, but that also makes it more limited. But one very important rule is that you should never ever delete facts. As I said, facts just accrue, because if we think about it, if facts are really sort of information about the past, then it's our only path to the present. If we delete facts, then we're lost, right? We don't know where we are and where we're going, really. And I think there's really no reason why in-place updates should exist any longer. It used to exist because disk was really, really expensive. So but today, disk is cheap. There's no reason to not have facts, all the facts that ever happened in the system stay around, right? I mean, this is how most I think all SQL databases work in them internally, right? They have the transaction log, but the only API that's exposed is like in-place update to our users. So we need to jump across a lot of hoops to try to have like auditing tables and tables for storing events, duplicating information in many cases. And Jim Gray said in this paper that the transaction concept in '81 that when bookkeeping was done with clay tablets and paper and ink, accountants developed some clear rules about good accounting practices. One never alters the books. If an error is made, it's annotated and a new compensating entry is made in the books. Thus the books are thus a complete history of the transactions of the business. Update in place strikes many designers as the cardinal sin. It violates traditional accounting practices that's been observed for hundreds of years. And I think this really means that essentially CRUD is dead. Right? We don't need update and delete any longer. We just need to create new facts, either like by bringing them in or derive them, or read. Read at any point. Store all information around instead of updating and like doing destructive updates. So add more knowledge and draw conclusions, really. That's how the world works, once again. That's what we do every day. Even if we might have like terrible memories that we would like to erase, right? It's something we work hard on it, like out drinking or something, but it's usually not that successful. And I don't know if it's really good in the long run. Patel also said that in his paper, accountants don't use erasers, that the database is a cache of a subset of the log. And once again, I mean, it's actually, you usually have the transaction log underneath. But what most SQL databases just gives us is essentially just a cache of that, or often just a cache of a subset of the log. So I really think it's important instead that we start working with the truth, with what's actually there, and that's the event log. So I think one of the best ways actually to make sense of all this is like to store facts ordered in an event log, like causally related. And in a way, a log is like a database of the past, instead of not just a database of the present that we are used to, but actually has all the historic information there. And the log sort of allows us to go on a journey in time, in a way. The log ID can be looked like as a concept of time that allows us to like travel across this timeline to make sense of what's happened and why we ended up where we are, and so on. So again, I think it's the succession of these causally related events now stored in the log that makes us gives us a great tool to make sense of the world, right? And you know, if you remember, this is really our definition of time, the causally related succession of events. The log also allows us to do things like time travel. I mean, since all history around, you can actually go back and do like auditing, debugging, and all of these. And it can be very useful for a lot of reasons. But one important question is, should we rewrite the past? I think the past is biased and subjective. I mean, it's always you know, also the winners that get to write the history books, and they get rewritten all the time based on new information. We knew more about what happened now than we did some time ago. We found new facts. And in computer science, we actually have the chance of actually going back and alter the books, the accounting books that Jim Gray talked about. But is that a good idea? It can be very tempting sometimes, but I think it's a recipe for disaster in most cases. Instead, we should derive new knowledge and append that to make sense of the world. I mean, it didn't go that well for Doc and was it Marty? Yeah. So I also think that we really need to shift our focus long term. I think actually it's been long coming, from data at rest and just focusing on offline data to data in motion. And because data in motion is really where the interesting things happen. And today, with most systems, or most users, it requires us to react extremely quickly on new information. And this means that we can't afford like storing it offline and have either like batch processes doing, and when we get a request, go off and fetch the data and do processing on it. We actually need to really like drink directly from the fire hose in many cases. And you know, streaming is a really hot topic nowadays, and it is for a reason, I think. You know, Spark streaming, I mean, the Lambda architecture and like things like reactive streams, there are some interesting talks about it here and so on. Time series databases, all these are on the rise because it's all tools that are driven by need to react on data in motion, the need to actually see the world as causally related events that are ordered. And I think it's great to have like ways of allowing time to evolve independently then, without sort of coordinating it much more than needed. But I think there is a need to sometimes actually do coordinate these event streams or these event logs, and because we need sometimes to agree on knowledge in the world across or multiple entities or data systems or data centers or whatever it is. So we need consistency. So the question is consistency then. What is that? It's really, I think consistency really means applying some sort of coordination mechanism. And the problem is that like too little coordination means that we violate correctness, and too much coordination means that our systems become very brittle, can be made available, and or become dog slow. So coordination is really, in consistency in general, is really hard to get right. And in general, I usually try to tell our clients that start with the minimum, right, and then add them as you go, because every single like constraint in terms of guarantees of data integrity and so on adds to like pushes down the roof, right, and how much you can scale, essentially, especially in a distributed system. So I really think that we need to start by defining our unit of consistency. What is the minimum sort of unit of consistency that we can live by? Yet again, like decomposing the system according to a lot of the things that have been said about reactive systems is really beneficial here. So try to like decompose it into small units in which we can actually have like a stable view, like strong consistency that we talked about. And the important thing is that this unit of consistency can never be partitioned, really. It can't be, you can't send half of it over there, half of it over there. It needs to be treated as like an atomic thing, that you replicate it as a whole, or you shut down as a whole, or you start up as a whole, and so on. And we're used to having one huge large consistency boundary, right? Like usually the SQL database. And that can work to some extent. I'm not saying that is all bad. Absolutely. Some systems, that's all you need. But in many cases, I mean, when you start having downtime or having a hard time like really getting the max out of all the hardware you have, that's usually because you haven't decomposed the system. You have like hold on too tightly to this consistent view. Okay. And Pat Helen, he talks about, he has like sort of a nice framework for thinking about this. He talks about the inside data, that's like inside this consistency boundary. That's our current present. Okay? The outside data is what he called the blast from the past. Let's all be always looking into the past then. So that's eventually consistent data. And between the services, you know, you have hope for the future. I just love that. And there are some good techniques that just arise. The microservices are really hot, and it's really just about common sense, right? It's really, first of all, a terrible name. It's really nothing to do with micro, macro. It's like really about trying to decompose the systems into things like services that does one thing and one thing well, and that are isolated, right? So you can manage them in isolation. They can die in isolation. You can upgrade them in isolation, write them in isolation using different teams and so on. But so within this microservice, though, that can be our consistency boundary. So within that, we can actually have full control over the present. But outside, we shouldn't even try, I think. It's always the past. And another great tool is like, you know, this aggregate roots. I don't know if you heard that in DD, like it's a common thing to model things in domain-driven design. Actually, that also applies very well. You know, an aggregate is like a group of domain objects, and the aggregate root is like the guardian that says, you can't touch my guys over here, right? You have to go through me, and he's like maintains the integrity of the whole group. That's also is a nice way of modeling sort of your consistency boundary to be sure that within this group of domain objects that I have sort of behind it, we can have full consistency without paying, I mean, the overall price, right, of trying to shoehorn everything in. Yeah, so within the consistency boundary, I think it's great to model this sort of persistence as a log, for example. And one pattern that have emerged the last years is event sourcing, which I think is a great abstraction on top of the log. It makes it easier to work with it. And you know, the event sourcing means that you log every state-changing event in the log. So everything that's sort of made, you can either store the commands, sort of that will lead to new facts, or you store the actual facts that enter the system. And since you have them all in the event log, you know, I mean, the event log allows for time travel, and it allows us to actually replay the log for auditing, for things like replication. If one node goes down, you can replay the log, materialize the component on another machine, and just let him continue. Queries, however, might still be hard, right? That's why we need patterns like CQRS, like command, what's it called? Command query segregation, segregation. Sorry, but that's sort of within these consistency boundaries. What about between? It's a zoo. It's just deal with it, right? We can't have any real guarantees within between these consistency boundaries, really. But it is really this zoo that gives us availability and scalability. When we can decouple them, decompose the system enough, then we can actually start to get, then we actually get tools to make our system scalable, elastic, and truly resilient. And to model this, I really think, yet again, we need to decompose the system, and we need to do it in two different axes. We need to decompose the system in time. That opens up for concurrency. A great tool here is, of course, the asynchronous message passing. And it gives us this loose couple, this like share nothing design. It opens up for resilience, location transparency, and these things. And at least if you decouple it also in this other axis, which is space. Space, if you decouple it in space, means that you open up for distribution, not just concurrency in terms of interleaving. We can actually run things in different processes on different nodes as well. So that's enabled location transparency and mobility. And if these things that you decouple actually are these atomic things, right, that are strongly consistent within and then moves as a whole, then you should actually have a quite nice, easily understood, intuitive programming model that gives you a lot of freedom to deal with the hard stuff, that scalability and availability. And this is how reactive principles really can lead the way, I think. Go and read the Reactive Manifesto if you haven't. That tells you at least the first steps you need to understand. But what about strong consistency then? Sometimes I think we actually do need strong consistency even between these services, but the price is just immense, right? So I think it's the wrong default. We should never start with that. We might end up there for a small data set, in the worst case. But shoehorning all your data into that, yet again, is a recipe for disaster. At least if you write medium-sized to large-scale large systems, which most systems are today. When they put on the internet, they're exposed to hundreds of thousands of users, perhaps even millions of users. So unless you know that your system won't ever be that big, or you think that you will actually don't succeed that well, then sure. But I think it's still the wrong way of starting, because it has a lot of implications how you design the rest of your design. Think about it as one tool that you can add on when you really, really need it, I think. And when we run distributed systems, and we're living, like as I said, like we all do now, we're actually living in the looming shadow of impossibility theorems. We all know that the network is really unreliable, and Fisher, Lynch, Patterson, in this classic FLP paper, actually proved that consensus is actually impossible. The paper is called Impossibility of Distributed Consensus with One Faulty Process. And it can be viewed through the lens of modal logic and knowledge theory, the work done by Joseph Halpern, where he talks about this ladder of knowledge. I find it quite interesting, actually. I won't go deep into this, but he really tries to explain what common knowledge. You know, we always take common knowledge for granted. But what is it really? So he defines this ladder of knowledge like S of phi, like someone knows. E1 of phi is like everyone knows. E2 of phi is like everyone knows that everyone knows, and then everyone knows that everyone knows that everyone knows, and so on. But actually, to reach common knowledge, actually you need an infinite number of I. You can never ever reach common knowledge if you didn't start with it, right? So what he proves is common knowledge is actually not attainable via protocol. You always need to start with it. You need to start with a common base, right? Syncing the clocks, like you can have probably atomic clocks. That's how Spanner gets away with it, by the way. But actually they can base it on shared common knowledge. You know, Google's big database, they have atomic clocks to sync between. But if you don't start with common knowledge, you shouldn't even strive for it. You should actually deal with it, with the fact that you can never reach that and have better approximations. CAP theorem is another impossibility theorem that proves that consistency is actually impossible, at least if you want to stay available. I don't know if you heard the CAP theorem, but out of these three, consistency, availability, and partition tolerance is something that you always have. It's mandatory if you run with a network. That means that you can actually just choose one out of two, consistency or availability. You can never get both. And this was proven by Nancy Lynch later. It was a conjecture done by Eric Brewer. But it was also like it puts a cap on what we can achieve. So impossibility theorems are useful, I think, because by saying what's not possible, it can actually point the way on what is possible. And this sort of like kicked off this whole trend of eventually consistent systems. I think Dynamo paper by Amazon was probably the one that sort of kicked most of this off. But then we had this whole NoSQL database trend, and that's good, right? But I think when we start dissecting CAP, I think it's been a lot of confusion about CAP. It was very influential, but it also had a very narrow scope, at least in the formal definition of it. So Peter Bayliss, in one of his papers, said the CAP has led to confusion and misunderstanding regarding replica consistency, transaction isolation, and high availability. And the problem is that strong consistency is actually not always required. It also often sort of ignores latency and these other things. And the things that, since partitions are actually fairly rare, I mean, I say they will always happen. It's a minute, right? But they don't happen every second. So why should we always pay the price for consistency to availability all the time? I think there is a need there's a big gray zone here. Everything is not like black and white. There's a big gray zone of interesting problems that can be solved between these two extremes. And Eric Brewer even argues for it himself in his paper that he wrote article he wrote for InfoQ some time ago, called CAP 12 years later. There's actually a need for more refined models. CAP points the way, but it's a very bad tool to argue about system design, I think. It's just too coarse-grained, too much black and white. James Hamilton said that the first principle of successful scalability is batter the consistency mechanisms down to a minimum. And eventually consistency is a great tool, right? But what does it really mean then? It gives us more headroom, absolutely, but how eventual? What does that mean? I mean, you need to start defining SLAs to make sense of eventual consistency. There are actually some interesting articles published about that. It gives us models for how to deal with to reason about eventual consistency. Peter Bailey's group at Berkeley have a model, have sort of released both software and a paper called what they call probabilistic bounded staleness, where it actually gives you a formal model to know like how eventual and how consistent do you need to be, and what are your constraints that you need to work in to meet both these guarantees. And once again, I think, as we already said, tracking time is tracking causality, and I really think that relying on timestamps is a bad idea, right? Because you have, even if you start with it, you will have clock skew and so on. So things like last write wins that some databases have, I think, is actually often leads to, you need to know that it will often lead to write loss. Just because wall time is not a good sort of tool for time, really. Instead, I think we should rely on logical time. And there are great tools in the history, in the computer science books like we all read, like for this. I mean, Les Lamport came out in 1978 with this paper, like Lamport clocks, that he defines like a global causal ordering between events. That's useful, but that was later sort of enhanced by Colin Fitch in the late 80s with vector clocks. It gives us, it sort of defines a partial ordering between the events. That sounds less powerful, but it's actually more useful because it allows us to detect conflicts between the causally related events. And this is how a lot of databases like React, for example, works. Causal consistency in general, I think, is a great tool. Because it gives us intuitive semantics. It gives us like read or writes and so on. And it's been proved that causal consistency is actually the best you can get with availability. You shouldn't even strive for anything better because it's not possible. But causal consistency is actually quite costly as well. I mean, you need to track metadata. I mean, who's talking to who's talking to who's talking to who. And if you have endless communication flows, it can actually be quite costly. So here again, I think we need more refined tools, and there's a lot of research going on there that can help us with this. It's not a golden hammer. It can actually be a good tool in the toolbox alongside the other ones. We all know ACID, right? So another good sort of mental model to have in the back pocket, I think, where the industry needs to embrace more is what like fashionable called ACID 2.0, right? But it also was from a paper by Pat Helland where he argues that really the goal is to succeed if the pieces of the work happens at least once, anywhere in the system and in any order. And ACID 2.0 sort of in this acronym sort of try to like brings together some of the most important concepts that we need to embrace I think as an industry. That is being associative, meaning that grouping, batching actually does not matter. It's okay to batch things. C stands for commutative, meaning that the ordering of things doesn't happen. So you don't need coordination there. It also opens up a lot for scalability and being available. Idempotency, I stands for idempotency, you know, that is that duplication doesn't matter. It's actually okay to send things more than once. You know, at least around once protocols are often like how message queues work, and there's at least an option that you most often, by the way, should strive for and turn off this guaranteed delivery option that's essentially just more or less a lie, right? Give me a baseball bat and I'll show you. D stands for distribution. just to make the acronym a bit more cool, I think. One tools are that's starting to emerge. There's actually concurrent research, but that we have embraced in ACA, for example, with Patrick's great ACA distributed data. It was used to call data replication. And REACA also fully embraced now. And there are other databases that are adding them, is conflict-free replicated data types. And you know, most SQL databases are key value stores, have historically been key value stores. And just key value stores just essentially just gives you a register, which can be useful, absolutely, especially if you have the right properties of being available and reasonably consistent. But we as developers are used to work with richer data structures. Like we used to work with maps and lists and graphs even, and sets and stuff like that. And CRDTs, conflict-free replicated data types, gives us the same, like rich data structures that have the same properties as these key value stores. They are fully eventually consistent. They will always converge correctly. And they compose. So you can have like a map CRDT, you know, with sets, with, for example, counters is another abstraction that can be modeled as a CRDT. And CRDT really embraces a simple concept, and that is that you have like that facts just accrue, right? Monotonically. You just add things. So if you can model a data structure where things just monotonically increase, meaning that you just add facts, don't remove anything, then you can actually model these type of data structures. And yet again, it's sort of essentially builds in the concept of time into the data structure itself. And I think this points the direction where we need to go. And as I said, this is not just research, this is real. You can just start using it today. And we use it internally in TypeSafe, for example, to build Conductor or like reactive application manager for consensus. It's working great. I'm just going to close with some interesting research being done by the Berkeley group around this, right? I think it was Joe Hellerstein that defined this CALM theorem. It stands for consistency as logical monotonicity. And they have a language called Bloom that sort of comes out of that actually makes time first class. And the interesting here is that they want to take the properties of CRDTs and actually put them into the language. And so the language can tell us when we need coordination. And so if we don't get a compiler error saying that you need coordination, for example, here you need to sync in with a SQL database or use Zookeeper or whatever. When you don't get a compiler error saying that, then everything just works without any coordination. You're like free to scale and to be as available as you want to. And I think this really points the way. We need to get time as a first-class construct into the language. Even this is just a toy language yet, but I think really it points the way. But in general, I think as an industry, we're just getting started. Time is such an important construct. We need to think more around how we should deal with it, how we should make sense of it in systems, because we just can't ignore it any longer, and we just break free of this illusion, right, that time is absolute, and step out of the Newton's universe, really. And I think we have a long road ahead of us, and it looks quite foggy out there, but one thing is clear, I really think time needs to be first class. So stay curious, and then thanks for listening. I don't know if we have time for questions. Else, it's 10. Else, just grab me during the day. If you see me, I'll be happy to discuss these things. This was like food for thought, right? More than I hope that it will open up for more questions than answers. So any. Okay. Yeah, sure. Okay.
I didn't knew that I will end up on the stage to ask a question. Anyway, so I really like your talk, and I think there's a lot of like food for thought, as you said, but I kind of really not so sure about the first motivation that you put it, and you kind of hand-waved that, oh, you know, time is relative, you know, we have Einstein and so on, and we cannot use it. But I mean, isn't this actually will, you know, start hitting us when we build a data center on a rocket ship, yes, and then ship it at the speed of light to the space? Because, you know, the other problems that we have seen is more because, you know, because there's latency, not because time is relative. And maybe, I mean, to be more concrete, you actually mentioned yourself Spanner, yes, and Google, which is based on true time, yes? That actually, it assumed that there is one time on the whole Earth, yes? And that they can actually measure the error and so on, yes? And actually, based on this, they have easier reasoning about this. So they, you know, they didn't, you know, hide the time, they actually modeled it better. So,
yeah, it's a good question. I mean, first, like, not everyone, of course, has the infrastructure and the money to make to like have your own satellite to synchronize in time. But also, I think what's interesting is that as you say, I mean, that they actually have. They have sort of a ratio, right? I mean, like the diff, I mean, and it allows you to sort of model time as a sort of a range rather than just something that is absolute. Sure, but I think that is using techniques like that can absolutely help us, I think. But I still really think that we need to rethink the model and the way we think about the world more than just trying to sort of like yet another time to just essentially try to like hold on to like this like a single globally consistent present illusion. I think, I mean, sure, you can get by to a certain degree, but for most I mean, regular systems, I think there are better and more sustainable ways of dealing with it. That's all in my experience at least. Since latency is now nothing that you can ignore. You could ignore latency up to like 10 years ago probably, or 20 years ago, but.
Thank you.
Is it on? Hello. Oh, it works. When you were talking about the event sourcing part, you said that you can either store the events or the commands. Is storing the commands not a nice way to create multiple universes parallel, because commands may fail?
Yeah, absolutely. I mean, I think they both have their place, right? Command and command sourcing is side effecting, and it should be, right? So it's a very different model than modeling just on event sourcing. It's actually based on facts that have already happened. So often, I mean, user input can perhaps be commands, like there's a hope for the future. The user hopes to create something eventually, and that will generate a fact that will then be persisted in the event log eventually, so to speak, if it was successful. So these are, I don't see these as like either or. I think they model very different things. But in my view, event sourcing is a lot more useful and a lot more true than command sourcing, which is a little bit on the side, right? I'd say.
Thank you.
Hi, I would like to ask, because all the things you say about this message passing and all the keeping state confined in a safe haven and all that stuff reminds me a lot of the original conception of object-oriented programming. And Alan Kay, which is one of the guys who created this approach, was asked about this. He said that it's more likely that way instead of the thing we have been entertaining this year. So in your eyes, you might say that we have lost a generation of programmers that misunderstood or were mistaught about this object-oriented concept, and we did something that we are recovering now and we are getting on track again.
Yeah, I think object orientation is something that probably was one of the things that was most misunderstood in our industry. I mean, when Alan Kay defined the object-oriented concept, he essentially, I mean, isolation, the message passing was at the core of it, and he's even said it multiple times, and even said, like, Yeah, well, like things like when he invented object orientation, he didn't have C++ in mind and so on. And I really think that is sort of going back to the roots of object orientation and message passing. You know, then you have ordered events communicating with like in communication flows across the system. Really gives us a much better platform to model things correctly, and also to model time. I think where it falls is where you don't have true isolation and how they like synchronous method dispatch between things. For a lot of reasons, of course, availability and brittleness and all the scalability running on multiple cores, but also as a way of, it's impossible to really model the succession of events, like if in a fully synchronous system. It's like at least a lot harder. So.
Okay, we have time for one more question.
What about facts becoming non-facts? There's like two ways to have that. One is that things have just changed, so it's a fact of the past. In that sense, it's still a fact, but it could also be a faulty measurement or faulty entry or whatever.
Yes, I mean, again, I think going back to the book and strike that out is probably not a good idea. I think this is yet again another thing that should be modeled using compensating actions. I mean, even if it was a faulty fact, it was still a fact, right? You perceive the world that way when you register the fact, and now you press no more. But that's also because you have gotten more information, right? So it's back then you still didn't know anything more than you did when you took the wrong decision. So to make sense of the world incomplete, I think we need to continue to add facts. That's at least my view.
All right, thank you, Jonas. Everyone, there's 50 minutes to the next session, so let's thank Jonas again.